here we go. Let's go, yeah? Standard model part 2. Okay, help me out. Let's finish up with up, down. Yes. Top, bottom. Well done, yeah. 6 quarks, yeah? There's 6 flavors of quarks, just like ice cream. Okay, there's 6 quarks. Flavors of quarks. What about the leptons, the 6 leptons? Correct. What are we missing here? Yeah, neutrino. Electron, neutrino, muon, neutrino, tau, neutrino. Yeah, well done. So once again, 6 flavors of leptons. Brilliant. Okay, and as you go across a generation, the mass increases, okay? Increasing mass. So as you go across, there's increasing mass. So a top quark is heavier than an up quark, right? Increasing mass. Okay, what are the charges of up, charm, and top? Well done, plus 2/3. What about down, strange, bottom? Well done, yep, minus 1/3. What are the charges of the electron, muon, and tau? Minus 1, yep. Charges of the neutrinos? 0, yeah, easy. Okay, good. There's some nice facts here. So the electron was the first fundamental particle discovered, 1897. First to be discovered, 1897. Okay, the first piece of the puzzle. The tau was the last to be discovered, sorry, the tau neutrino in the year 2000. Just some facts in the year 2000, okay? Just over 20 years ago. Okay, so what are all these particles collectively called? All these? Yeah, fermions, well done. So these were all called fermions. Yep. Okay, you obviously also need interactions between the particles, okay? There's got to be a way for them to interact. How do they interact? Let's say an electron with another electron via forces. Okay, there's 5 force particles. Got the photon, gluon, W plus and W minus, the Z, 0, and the Higgs. You got 5, yeah? They signify charges, so 0 means I've got 0 charge, plus charge, minus charge. Okay, there's 5. What do we call these collectively? Yeah, well done, bosons. Okay, W stands for weak. Z stands for 0, it's got 0 charge, right? Stands for weak, Z stands for 0. This is going to sound silly, but it's just a convention. The W plus boson is used in radioactive decay. It's used in beta minus decay. W minus is used in beta plus decay. Right. So, okay, photon, what forces are carrying? Well done, EM force. What about the gluon? What am I doing? Strong force here. Trying to do Arnie poses here. Oh, what about the 2 W's and 1 Z? What force? Yeah, weak nuclear force. Lucky last, my good friend here. What does he do? Well done, yeah, mass giver. Well done, yes, mass giver. So these are the bosons. Okay, and that is the standard model of particle physics. SMM. Okay, periodic table of existence. Just some facts about the Higgs as well. The Higgs, per billion collisions between two protons in the Large Hadron Collider, only one Higgs is produced. That's how rare it is. Its lifetime is 10 to the minus 24 seconds. 1/1,000,000,000 of a trillionth of a second. Very rare. Yeah. Z boson that's used in radioactive decay. W and Z radioactive decay. Yeah, decay. Yeah. The Z is basically used for momentum conservation. So that's actually used, if you write this down, for momentum conservation, just for the numbers to match. Momentum conservation. Okay, these here, radioactive decay. Of, yeah, radioactive decay. Okay. So that's the periodic table of existence right there. How to build a universe, that's how you build a universe. Nice history. Take a look, that's what I discovered. From the very first, the electron, to the very last. Okay, it's all been observed. What does that mean for the theorists? Party, happy, excited. Proves that the maths is correct. Okay? This maths here. Okay, here was the issue. More particles started popping up in detectors around the world. You don't need to know this, thankfully. Hundreds and hundreds and hundreds of particles, baryons, mesons, they've all been catalogued. That's how many particles there are. This is called the particle zoo. Yeah, there were so many particles being discovered. This guy here, Isidore Isaac Rabi, the guy who discovered MRI, said that, who ordered all that. That's how annoyed they were getting. Robert Oppenheimer, founder of the atomic bomb, that's what he said. They were getting really annoyed. There was a lot of particles popping up. They couldn't explain it. Here's what this guy said. What was his name? Yeah. It was really getting people worked up. Forces, I talked about these. Electromagnetic force comes from electricity and magnetism. It's found in motors, light sources. Okay, it keeps electrons stable in atoms, okay? Strong force holds together quarks. I mentioned this before. Keeps protons and neutrons stable. Weak force, radioactive decay. That's why the sun shines. Gravity, that's not in the standard model. Unfortunately, we can't work out how to put gravity inside it. But if there was a particle, it would be called the graviton. You can write this down if you want. I'll put this here. Small g, or big G, big G. Let's put a big G, zero charge, graviton, question mark. We don't know. No one knows yet. Okay, there you go. Summary. Yeah, so there was a point in time, during the Big Bang, as I mentioned before, where all the four forces were once unified. And physicists are after a theory called a grand unified theory to explain everything in the universe, including gravity. At this point here, unification. Okay, they branched out, all the forces eventually branched out as the universe condensed and cooled from the Big Bang. Still working on that, not me anyway. Just two important theories. The syllabus isn't explicit, but it's just good to know these. There's a theory called quantum electrodynamics. It basically explains how particles interact with the electromagnetic field. So if you look here, time is here, space is here. Two electrons, when they come close to each other, what do? Yeah, repel. And the way they repel, they exchange a photon. That's called a Feynman diagram. Named in honor of Richard Feynman. These guys won the Nobel Prize for their work on that. Okay, fermions, they're straight lines. Photons and other bosons, they're wiggly lines. Usually the Higgs is dotted. But Feynman diagrams used to show how particles interact. Okay, and there's something called quantum chromodynamics. Chromo means color. It basically says that quarks have this property called color charge, even though there's no color. It's just a way to label quarks. Okay, they're color charged. So let's say a baryon has to be colorless. The quarks have color, let's say red, green, and blue. When you put them together, you get white, neutral. Well, it's just a way to keep track of quarks in particles like baryons. Mesons, quark-antiquark pair. Red, anti-red gives you color neutral. I cancel out. It's just a way to label quarks. So that's what color charge means. It's a labeling mechanism.
Is there a name for like the top level of quarks, like up, charm, or top?
No, they just call them generation 1, like this, 2, 3. No, no. Yeah, if you take a look, it's a nice schematic there. Americans mostly discovered all the particles there in the standard model, except the important one, the Higgs, Switzerland, LHC. But yeah, Americans. Oh, what's the Higgs? Yeah, predicted 1964 through some maths. It basically allows for what's called electroweak symmetry breaking. Electroweak symmetry breaking. What does that mean? It allows for electromagnetism to separate from the weak forces. Allow for photon, in other words, and W plus and minus Z dot Z0 to separate. Okay, think of like a this is called a Mexican hat potential. At the top, there's perfect symmetry. Once it rolls down, symmetry is broken. It's an analogy. Okay, so the universe, just after the Big Bang, was perfectly symmetric, yeah? You can't tell apart a photon from a gluon, let's say. After the Big Bang, sometime after, asymmetric. Yeah? 2012 discovered. That's a great animation there. Alright, so there's a field throughout all of space called the Higgs field. It's made of Higgs particles, and particles interact with the Higgs field. When they interact with it, they get mass. So a photon has no mass because it goes straight through the Higgs field. Right, whereas quarks have mass because they interact. That's a good way to look at it. Have a read of that. That's called the celebrity analogy. It's a great way to understand it. Next. Makes sense? So a crowd of people coming towards someone, that's like a particle gaining mass. That's an analogy. Yeah, how's the Higgs made? Two protons colliding in a particle accelerator. That's how you get Higgs. Yeah, there's 4 main different ways. You don't need to know this. There's 4 different ways to make Higgs as well. Yeah? There's 4 different possible ways you can get a Higgs. You can have 2 gluons come together, interacting, 2 quarks, quark, antiquark, etc., etc.
You know how you said there's 4 ways to make Higgs? Is that like for example, the gluons, they repel and make like a Higgs in between, or is it
Gluons, they come together and make other particles. Other particles in the Higgs.
You know how you said there's the particles come together, they repel with the photons? Is it like the same thing?
Yeah, sort of, yeah, exactly. Yeah, on the bottom. No, you don't need to know this. You don't need to know this, no. I'm just showing you how to make a Higgs. Right? Yeah. Okay, you take a look. Leptons only interact with the weak force. Weak force. Quarks interact with all forces, yeah? Sorry, leptons interact with electromagnetism and weak force. What did I say? Quarks interact with all forces. Leptons, you've got the neutrinos, only the weak force, only radioactive decay. Electron, muon, tau, electromagnetism, weak force. Higgs, all particles, except for some. That's the Higgs field. Okay, particles get slowed down and they gain mass in the Higgs field. Okay. Yeah, how was the Higgs discovered? Data analysis, a lot of data. Whenever you see a bump in statistics, that means a possible discovery. Okay, 2 experiments called Atlas and CMS. They found a dip, a bump in their data at about 125 GeV, gigaelectron volts. That was the Higgs that they found. Just statistics. That here, there's about 3,000 scientists working on one of the detectors at LHC in Switzerland. 3,000. The beauty of collaboration here. If you take a look. Time machine? Time machine?
Is that a time machine?
No, it's a detector. Part of the detector. Here's the beauty of collaboration. Look at that. One of the papers they published. Look at how many contributors. Just keep looking. 3,000 scientists working together. It's amazing. All that. How many countries? Australia's one of them. I think there's about 80 countries overall. Yeah, that's the beauty of science, just coming together. Doesn't matter where you're from. Yeah. Yeah, I was really excited about this recent discovery. They found, so the Higgs boson can decay. Higgs boson can be made in 4 different ways typically. One of those ways was found experimentally in May. Okay, others were, some were theoretical. This was theoretical. They detected it experimentally. Okay, so just read that. It's just one of the ways that Higgs decays. So you can't really directly detect the Higgs, it's too short-lived. You can only detect it indirectly via particle decay. Yeah, that's a very small number. But that was very exciting seeing that. Right, so that means the Higgs decays into that, which decays into that. Okay, photon, Z boson, photon, antimuon, muon. So you can only indirectly detect the Higgs. That's what that's saying in a nutshell. Okay, that's the actual collision. Computer graphic. Yeah, there you go. Different ways Higgs can decay. Freestyle analogy. Okay, so most common way to make a Higgs, 2 bottom quarks coming together. When you smash together 2 bottom quarks, you can get a Higgs. Most of the time, 58% of the time. Let's talk symmetries. Symmetries in the standard model of matter. Let's talk symmetries. What's symmetry? How do you define it? Anyone? Funny things to describe. If you take something, let's say a sphere, and you rotate it, looks the same from any direction. That's symmetry. Okay, it's a property that's conserved, no matter how you look at it. So let's look at symmetries. Here's an example. Electron, muon, and tau. So electron, muon, and tau. Whenever you see these in nature, you'll see a corresponding particle. Muon, neutrino. Electron, neutrino, muon, neutrino, and tau, neutrino. So they always come in pairs. Whenever you see these in nature. So that's the first symmetry in the standard model. Okay, leptons, they come in pairs. They come in pairs. Okay, there's another symmetry. Actually, this is sort of linked to this. So let's suppose you have a neutron. So neutrons can actually decay into protons. Why? Neutrons are unstable. Protons are actually stable. They don't really decay. They've got a very long lifetime. So for a neutron to decay to a proton, it also gives out an electron. What would accompany an electron in this case? Yeah, electron neutrino. Sorry, anti-electron neutrino. Sometimes. conservation charge. Conservation charge. Okay, leptons, they come in pairs, as you can see. Yeah, you don't need to know this, it's just nice to include. There was a great mathematical theory, 1960s, 1964. Two guys, Gelman and Zweig, they came up with it's called the eightfold way. A way to categorize things like baryons and mesons, and hadrons. They could categorize them according to things like charge, spin, and they were able to predict particle discoveries from that. That was significant. Particle discoveries in detectors. And sure enough, years later, so these are mathematical constructs, they detected them amazingly. Right? Sweet that. That's nice somewhere there. Okay, that's the power of maths. You can make great predictions way before the particles discovered or seen in nature. Something like that. Yeah, what's next? Okay. What's next for standard model of matter, aka what are the limitations? So just like any theory, there's always going to be limitations. Always going to be limitations. First one, why are there 3 generations of fermions? And why is it there's only, leptons as well, fermions. Okay, why are there 3 generations, for example? Okay, and why, let's say, is the top quark, I think, 2,000 times heavier than the up quark? Okay, that's called the hierarchical problem. Hierarchy, heaviest to lightest. So that's one question. Why are there 3 generations, for example? Yeah, come on in. Almost towards the end. Come on in, Pakistan. Yeah, right, almost towards the end. All right, so why are there 3 generations of fermions? No one knows. That's still an outstanding question in particle physics. Number 2, is there a grand unified theory? Can we unify gravity? Can we put gravity into this mix? We don't know. Can we include gravity? One possible answer, string theory. A beautiful mathematical theory. That's very deep to me. Yeah.
So you know how the electron neutrino has no mass? Do the other generations have any mass?
Okay, these here have no mass. Actually, very small mass. Just a very small amount to the point where it's negligible.
Even the neutrino?
Yeah, all neutrinos, roughly
So
massless.
it's not detectable or is it
Indirectly detectable.
indirectly?
That's number 2. Number 3. Watch this. Sparkles. If you thought that was enough, there's a beautiful mathematical theory called supersymmetry. It predicts double the amount of particles in the universe. It says that for every fermion, there's a boson, every boson has a fermion. A beautiful balance. Let me show you. Supersymmetry. So it's taking this symmetry a step further, also known as SUSY. Yeah, no, seriously, it's called SUSY, supersymmetry. Okay, for every fermion, there's a boson. How does this work? Let me show you. Okay, here's how you name them. Every fermion partner has a boson partner. Here's how you name them. You put suffix eno. Sorry, my bad. Prefix. Yeah, S. Let me show you. Quark, squawk. Electron, selectron. Muon, smuon. That's supersymmetry. Okay, every quark has a squark. Every electron has a selectron. Okay, it's one more beautiful balance we can put in nature. One more beautiful theory. We can double the amount of particles. Hasn't been detected yet experimentally, sadly. It's theoretical, sadly. Okay, every boson partner has a fermion partner. And here's how you do it. You add suffix eno, e.g. photon, which is what light's made of. Light's made of photons. Photino. Higgs, my favorite, Higgs xenon. And that's how supersymmetry works. Absolutely beautiful.
What's the purpose of
This is a great theory because it explains unification. This could probably answer this. In the early universe, just after the Big Bang. Also, yeah.
How is dark matter, dark energy being detected?
Indirectly.
Indirectly.
Yeah,
Just like how we should do it indirectly.
that's right. Okay, what's the nature? So another limitation of the standard model of matter. What's the nature of dark matter and dark energy? We don't know. So most of the universe, 73% is dark energy. We don't know. We don't know what it is. Are there particles? Are there something else? About 23% dark matter. Us, we're about 0.4% of the universe's mass. So a very small amount. We're basically the exception to the universe. Think about it. Just a very small. Us, stars, galaxies, are about 0.4% of all the mass. We don't know what the rest is. Nobel Prize waiting. Maybe you someday. Inshallah. We don't know. Dark matter, this guy here, I'll tell this to the execs later. It's not G-rated. This guy here, as you can tell, had a bad temper. His name is Fritz Zwicky, Swiss astronomer. He'd lose the plot a lot of the time. He proposed dark matter, and the way he proposed it was, some galaxies weren't turning at the right rate, okay, based on the amount of mass they have. Okay, so it's like a missing mass, and he dubbed it dark matter. So missing matter in the universe. It didn't account for galaxy rotation. For a galaxy to rotate properly, there has to be matter. Certain amount of matter. Couldn't find it. That's supersymmetry. Visually. Beautiful mathematical theory. That's what we're made of. That's the hypothetical world that hasn't been discovered yet. Absolutely beautiful. Let me know if you see it, yeah? Haven't seen it yet. Yeah, you can think of them as like mirror particles, shadow particles. Okay, whenever you have a Higgs, you have a Higgs xenon. If you have a quark, you have a squark. Well, that's how it works.
So are there anti particles?
Correct, there's anti-Sussi particles too. Okay, you don't need to know this, just beyond the syllabus, but mathematically, it's just like an operator, mathematical operator, acting on, let's say, a boson or fermion, gives you their partner. The maths works beautifully. Gives you the symmetry that you see here. And yeah, Ramid asked, this is why supersymmetry is great, why I love it. Because if you go back in time towards the Big Bang, all forces unify perfectly. There's a perfect unification. Whereas without supersymmetry, that's what the standard model looks like. Yeah, string theory, another nice theory. This could probably explain things like why gravity doesn't fit into the standard model. Okay? It doesn't explain gravity. String theory could explain why. String theory proposes that all particles are made of strings of energy. And the faster the string vibrates, the string, the different particles you get. Different particles vibrate different frequencies of vibration, yeah?
So it builds on the way particles vibrate?
Correct. Yeah, so a string that's vibrating really fast, that's going to have a high mass particle, like a quark. Strings that don't vibrate much, let's say, electron, low mass. And for it to work, you need extra dimensions. Okay, so this is according to what string theory says, that's an electron, photon, quark. They're strings. Strings of energy. Yeah, I get asked this a lot. That's how long, theoretically. Hasn't been discovered yet, it's beyond reach of experiments. Why? It's called the Planck length, it's too small to see so far. So the LHC in Switzerland, isn't able to detect it because the energy is needed to get into this regime is very high. It's very, very high. You need at least 10 dimensions of space too. We live in 3 dimensions. Question is, where are those dimensions that we can't see? Theories propose that they're called up. They're called up very small. Like this. Possibly. So string theory is a way to get a gut around unified theory. So combine everything together, yeah? You've got different types of strings too. I'll put these up on Teams, yeah? Just for information, I love this. It's a real book. Yeah, no evidence so far. And here's an even crazier number. String theorists have worked out there's 10 to the 500 ways to curl up these dimensions, which is messy. Which one corresponds to our universe? That's the other question. Right? And that's going crazy there. Yeah, so that's it. So that's the standard model. That's what we know. Horizons are being broadened now. Okay, is there supersymmetry? Is there dark matter that we can detect? Are there strings? Are there things like monopoles? We don't know the answer. Right, now on to me now. Yeah? Special moment. I study this. That's my regime in particle physics. Okay, the smallest of all scales. What do? I study this thing here. Where is it? Can't see it. That's right. It's the Higgs. It's one particle. Okay, it gives mass to all the other particles in the universe. It's a very important particle. I work at the School of History and Philosophy of Science, University of Sydney. That's my supervisor. Top bloke. Yeah, that's what I do. Yeah. What does my research involve? Well, I do data analysis, philosophy, history, and physics all in one. It's very broad. Hey, not many people working on this around the world, so I'm one of only a few working on this. Very exciting. But yeah, it's just understanding the Higgs in terms of its statistics, its maths, its history, philosophy, all in one. See that? That is that. But in maths. That's called the standard model. You can put it on a t-shirt, that's the sign of elegance. This,
That entire thing is the standard model.
that's the standard. That explains everything in the universe except for gravity. If you want to know why the sky is blue, let's say why DNA is the shape it is, you can use that. Anything you can name, you can describe it mathematically. If you had a super powerful computer, you can work it out. Well, to me, it's simple anyway. Absolutely beautiful. Yeah, spin-offs, I get asked this a lot. Why do particle physics, theoretical particle physics? There's no benefits. Well, there is. World Wide Web came out of there. 1987. Yeah, Tim Berners-Lee, computer scientist at CERN, the European Organization for Nuclear Research, Switzerland, wanted a way to connect scientists around the world with data. Particle physicists invented the World Wide Web. That's a spin-off. First X-ray color imaging came from the Higgs discovery, Higgs boson, 2012. That's a full X-ray. So there's 2 spin-offs right there, very important. So medicine, computer science. I get asked this as well.
So what about solar power? That came up.
That came from Einstein.
Sorry?
Yeah, Einstein's theory.
Yeah.
Roughly. Photoelectric effect. Yeah.
I'll contribute to that.
Right, here, lifetime of the Higgs, as I mentioned, it's about 1 trillionth of a trillionth of a second. It's very short-lived because it's very unstable. But we can indirectly detect it through other particles. That's how we discovered the Higgs. Indirect detection.